Hi, and welcome to Venus Aerospace High-Speed Flight series, where we dig into all the technologies, processes, and things that it takes to go fast. I'm Dr. Andrew Duggleby, the CTO and co-founder of Venus. And on this first episode, we wanted to go really just an overview of what we're doing at Venus, but in particular, what's a jet engine versus rocket engine? Why would you choose one versus the other? What does it mean to be hypersonic? And what is this rotating detonation engine thing, and why does it unlock the hypersonic economy? As well, and just finishing with Venus plan. So kind of jumping right into it, jet engine versus rocket engine. Right? In the end, this is that fire triangle you might have grown up hearing about when you were a kid. That in order to have a fire, you need three components. You need your fuel, you need an oxidizer, and then you need some sort of heat source or a spark, or rubbing sticks together for if you're out in the boonies. Right? So jets are getting their oxidizer from the air and the atmosphere. And so it's the oxygen buried within the air. That makes you an air breather, a jet. A rocket engine carries it. Now, normally because rockets is what we use to get up into space, but we have many rocket applications where we don't go all the way up into space either. In the end, you're carrying something. Now, orbital rockets will almost always carry liquid oxygen. And so that's the most common oxidizer for a rocket system. At Venus, though, we're carrying hydrogen peroxide, which is H2O2. It's basically water with an extra oxygen, and that's what happens. It kind of splits into water and oxygen, and you use the oxygen for your combustion. And there are others, right? If you're a satellite, you might be using N2O, things like that. So that's really where it starts off as jet engine versus rocket engine. And then all of these systems, in the end, the idea is you're trying to take this fuel, you're trying to make heat by combining it with this combustion process. And then once you have heat, you're then trying to make thrust with it. So in this process, you have to suck, squeeze, bang, blow. It's this thermodynamic process, easiest way to say it. And so I'm going to draw it what that looks like for a rocket engine. And so a little small rocket engine here, throat and a nozzle. There's a throat and a nozzle. And so inside this rocket engine, this is where you'll have your fuel and your oxidizer meet. You'll start it with a spark, it'll then be self-sustaining, and it's reacting and sending out really hot exhaust. But what's happening in that process is you have high pressure here. So kind of like the meteorologist, I'm going to use a circle H to say high pressure, because you're burning and you're actually constraining it with this throat. That helps build the pressure here. And then whether you're going to the atmosphere or outer space, you have low pressure. And so we go from high pressure and hot through a nozzle where it becomes sonic, and then out back into the nozzle, it's even faster than that. And so you're basically shooting things out really, really fast, and that gives you thrust. Okay? And so writing this down, suck would be draw things in. So we shove them into the rocket engine. Squeeze. You are building pressure with a nozzle, and so a rocket engine will usually use pumps to kind of keep the pressure, keep pushing. And a lot of times those pumps are powered by side reaction. When I dive into a deeper version of jet engine rockets, I'll get into all that fun stuff. 3 is the bang. This is the combustion itself. And then 4 is blow. Right? And so that's the general way that you go from a chemical reaction, making, taking fuel plus your oxidizer and heat, right? You make more heat, and then you convert that heat into thrust. Okay? And so then, as we then talk about a jet engine, we'll get into how a jet engine's doing all this. Okay? But first, I actually want to start off and say rocket engines are how we actually went hypersonic first. And so this is a rocket engine on the back of the X-15. People remember the X-1, Chuck Yeager, breaking the sound barrier with a rocket-powered plane. This was the first system to go Mach 5, Mach 6, Mach 7. There's a human on board. It was reusable. So when people say, oh, hypersonics are new, it's actually, no, hypersonics are old. Hypersonics are old. And so this was in the 1960s, 120 missions above Mach 5. And then you can think of the space shuttle. Space shuttle went Mach 25. That's orbital speeds. And as it descended into the atmosphere, it was then going Mach 18. And it would slow down gradually as it flew across the entire Pacific, across the United States. This 30-minute flight of the space shuttle, most of that hypersonic. So hypersonics are old. Hypersonics are old. So when we at Venus are talking about the new hypersonic era, or this unlocks the hypersonic economy, we're talking about something that's no longer just a government research test. This is how can we do this cheaper, more effective, and then eventually talk about moving people across the globe. So that's where it starts. So to talk about how you might do this cheaply, let's first go into jet engines and how you would do this at different regimes of flight. So I've got a graphic up here that's talking about this is a jet engine, this is a ramjet, and this is a scramjet. So a little bit back to the suck, squeeze, bang, blow, but at first I need to correct this one on the top. And so what you actually are seeing here are a bunch of compressor blades and then a combustion chamber and a turbine. So suck. Well, if this aircraft is flying subsonically, air can actually be drawn in. It can actually be sucked in. But like I said, I need to add a little piece right here, which normally this is connected to a fan. I'll draw kind of like this. Okay? So you might have heard the word turbofan, and where it's a turbine driving a fan. Almost all aircraft have this. So your passenger aircraft will have a really big fan. Now it's still encased in a cell. You may have seen turboprop, where it's actually just a propeller, but it's still driven with a gas turbine. In any case, you have a fan that's the work done by the engine is mostly used to drive the fan. So a lot of the propulsion is coming from the fan itself, not exactly from the exhaust. But it's still the same general idea of sucks, the air is coming in, squeeze, these compressor blades are compressing the air, and then mixing with the fuel, you then have your combustion, that's the bang, and then blow. Now, these blades, these compressor blades, need to be powered by something. And so what this turbine is doing here is actually stealing a bit of the energy from this hot exhaust to drive the turbine, right? To drive the compressor blades, and then also drive the fan. Right? So suck, squeeze, bang, blow. Now, when you start flying fast enough, you actually don't need any of this stuff. In fact, you can just have the shock wave. So this is on a ramjet. These are the shocks. So once you go supersonic past Mach 1, you generate a shock wave. Behind that shock, you actually get a higher pressure. And so when you have enough shocks, you can kind of see the blue curves here, you generate enough pressure where you don't need any blades. It's high enough pressure to then just mix with the fuel, this is hard, but just mix with the fuel and then exhaust out the back, almost just like that rocket engine, right? So we built pressure by not our turbo pumps shoving fuel and oxidizer into this chamber, but we built pressure through shock waves. And then the scramjet, which really just means the supersonic combusting ramjet, what we're doing here is we don't let the air slow down below the speed of sound. So up here it was below the speed of sound. Here it's still above the speed of sound, and then we would combust this. Now I'm not going to talk about this too much in detail in this episode because scramjets are really hard. We humans have done this, but scramjets are really hard. So I'm going to basically ignoring it for right now. And if you are interested in more, follow kind of the deep dive as I go into more of this. So I'm really just going to talk about turbine-based combined cycle, which is combining this with ramjet, and then rocket-based combined cycle, which is combining a rocket with the ramjet. Now, the reason I'm going to talk about those two configurations is because, in the end, you have mass times acceleration is thrust minus drag. Okay? Now, if you're a rocket, you might say, well, I'm not staying in the atmosphere too long, so a rocket engineer would kind of ignore this, not really, you'd have a correction. And then you would figure out, how much thrust and then how much propellant you need to carry, go forth. But for those of us staying in the atmosphere, ultimately we're still fighting that drag. So drawing this out for a vehicle though, and so if this is speed, which I'm going to use just speed as Mach numbers, so if there's Mach 1, there's Mach 2, 3, 4, and 5, I'm going to draw the drag. So the drag really picks up around the sound barrier. Some vehicles can shift a little bit based on what you're doing, but it's basically, right there at the sound barrier, and then it'll fall off and come down slowly. Okay? Now, the thrust with that jet engine up top, and it can handle, as long as you have a nice inlet, it can handle supersonic flow. This is going to do something like this, and then I'm going to have a drop off here, and then there is where your ramjet would start. So this is really depicting the primary challenge behind turbine-based combined cycle, which is you have two things. You have one right here, and they call that the pinch. which is my turbine is barely making more thrust than the drag. It's barely overcoming, it's barely accelerating. It's called the thrust pinch. And then here, unless you do something, you could see there's a gap. And so that's the thrust gap. Now, if you solve that problem, then it might only be a pinch, but primarily that's the first thing you have to go do. But on top of all of that, air is not free at this speed. And that's a little bit where we have to then talk about hypersonics and what is hypersonics. And so when you're going this fast, the challenge then becomes the heat that you generate. So think of energy, skin friction on the vehicle. It's got some drag force. And then force times the velocity is a power. And so whatever that drag force, F drag times the velocity, that's how much power is being generated in just friction. And that's going to add heat to my skin, to my vehicle. When I'm flying for long distances, I can't just carry enough coolant to continually cool down the skin. It doesn't work like that. And so ultimately, you have to reject all of this by temperature. And so, if you've taken any radiation courses, that's sigma T to the fourth, but really this is just saying I'm rejecting the temperature. And so in the end, this drag friction, though, builds up with a couple coefficients. So I'm just going to simplify it here for this level of course, just to say this goes like rho v cubed, once you kind of calculate all of it. And so you have a condition where you might want to be flying. So back to this kind of speed, and then I'm going to draw this versus altitude. You actually might want to be flying this line. This might be where rho v squared, which is dynamic pressure. This is how much pressure is on your wings. You might be really happy at this point. But the temperature, again, which would be the quarter root of all this, the temperature might build up to a point here that you're not happy with. So we at Venus, we're trying to keep this below 900 Fahrenheit. I want to stay with titanium. And so we would say, hey, this is my top speed at this dynamic pressure. Another system might be trying to fly a little lower, a little thicker dynamic pressure. So let's say this is 400 pounds per square foot. This might be, say, 1,000 pounds per square foot of air pressure on the wings. And that temperature curve might be closer to, say, 2,000 Fahrenheit. This top one's Fahrenheit as well. So you have this problem that air is not free. So if you have to fly low enough to get your air, because this is altitude, air gets thin up top. So if you're trying to be a jet engine and then transitioning to ramjet, you may not be able to fly this high because the air might be too thin. And so you have this trade-off between heat and oxygen. So the real definition of hypersonic is when heat becomes your primary issue. Right? And generically, we'll say that happens around Mach 5, but that's not true. Okay? You could be Mach 4, Mach 3, and flying so low that heat is just smoking hot. That would still qualify as hypersonic, again, when heat is defining your number one problem. You could be at Mach 6 at really high altitude, and heat might still be okay. It might not be your major problem. You might be paying attention to it, but it's not your major problem. And so that is the definition of hypersonic. And so it's ultimately, how do you go from Mach 0 at standstill? If you're going to use a turbine to help you get up to that speed, then you've got to solve this pinch and the gap, and then ultimately get into random combustion, or like we're doing at Venus, you can use a rocket engine. So this is the fancier version of the plot. And on the deep dive, I might go into a little bit more, but this is really now showing you kind of more, less just me drawing on a board, but more particular math behind it. You can see the metallic limit. That might be the hottest metal you can think of where that temperature line might be. I've drawn here the titanium line. That might be like 900 Fahrenheit, something like that. In fact, there's SR-71 that was titanium and flew at Mach 3. And so it was fairly happy. And the top of this blue curve, that top limit, that's basically where, hey, there isn't enough air pressure for me to actually fly. And so if I'm a rocket, it's no problem. I'm just going to blast through this and get on up. I've got a rocket engine and ways to control it. But if you're a vehicle, you really need to stay into this. So if you're a jet engine, you really need to fly in this gray area where you have enough oxygen and you can get to that ram start. You can shut off the jet engine, switch over, and get to ram start. And then otherwise, you got to do some sort of trick. So the SR-71 was a ramjet. That was turbo ramjet. And so that's why I was able to cheat and go a little bit higher than I have this line shown. For us, we're using rocket-based combined cycle, so we use that to cheat in order to fly up here. So here's kind of the Venus profile. Here's Mach 4, here's Mach 6. Now, because we have a rocket engine, we could keep flying all the way up to Mach 9, but it won't be the most efficient flight. It won't be the longest range flight. So this really represents, here kind of a sketch here in pure numbers, what's happening with speed and altitude and heat. Again, if you're an air breather, turbine-based combined cycle, you got to be down here where it's really, really hot. And then as a rocket-based combined cycle, we can be up here where it's standard materials. And then we're able to achieve that RAM condition. Now, rocket-based combined cycle is not a new idea. It's actually quite old. So what I want to talk to you next is kind of the final point of this, and then share a little bit of our plan to Venus, is what is the detonation engine? It's a rotating detonating rocket engine, and why that allows us to solve this where a standard rocket engine couldn't. So I have a couple videos for you. And the first one, this is a detonation engine. I'm going to go ahead and erase my little turbine propeller. I don't need it for the rest of this. And the ring of fire that you're seeing there is about 4 inches, and this engine is about 2,000 pounds of thrust. And we're using jet fuel and hydrogen peroxide. And so in this ring, we have pushed fuel and oxidizer, so jet fuel and hydrogen peroxide, and we've allowed it to detonate. So instead of having a column or a cylinder of fire, we turn it into an annulus, and then we let it transition into detonation, which is supersonic combustion. So you take a look at this video. This is actually a high-speed camera view looking straight on into that engine. And you can see these detonation waves going around and around about 10,000 times per second. So it's very unsteady, but very fast. And so to us, it just looks like this pretty smooth, yet really thrusty system. Now, what you're shown here, this is our test stand here in Houston. This engine is all just heat sink copper. And we do that first for to do quick iterations in copper. Once we have a design we like, we then switch over to 3D printed systems. And this is then an engine test that we just released. We actually did the work in the fall in partnership with DARPA. We were able to finally release it in the spring. And we have this detonation engine now running for like 40 seconds. So we've solved the heat issue, we've solved the stability issue, and this is really maturing the detonation engine. Now, the reason this works great for rocket-based combined cycle is because it's now a ring of fire, not a column of fire, and it's unsteady. This mixes really, really well with the air, and we can use that to mix with the air and then achieve a RAM start earlier. So this final video, and then I'll show you kind of an animation of the full stack up. This would represent us at a Mach 2 condition. You can ignore the water, that's just us making this a cheap experiment. But this represents air and the detonation engine mixing together at about a Mach 2 condition. And it mixes it really efficiently. That was the big aha moment from our experiment. I'll dig into deeper details later on kind of a deeper dive into this detonation engine and why this is, we'll talk about mixing lengths and all sorts of things like that to show why this finally unlocked. And when we hear Venus, we say this is unlocking the hypersonic economy with this rocket-based combined cycle. And so just an animation. At rest, you're sitting on the runway. We light the detonation engine here. That's actually inside this full engine. And yeah, we take a little hit on efficiency here with the RAM. This is the RAM burner sitting behind it. But we do get exhaust, we do get thrust, and the air is actually being drawn in, right? Suck, squeeze, blank, blow. So it's being drawn in. Detonation engine is actually adding pressure and temperature to that air. It's actually going sonic right here at the throat. And then once we are up at altitude and then we start going supersonic, we now have enough pressure that we can light the RAM burner. The RAM burner, we're working with a company called Volantra. They've got a RAM burner. It's a wonderful partnership. And so now we have both the detonation engine and the RAM burner active, right? So no transition, no doors that have to swing shut, nothing like this. As we get to higher speeds, we're getting more compression from the shock wave, which means we need less of the detonation engine, so we start drawing back on the detonation engine. And then eventually, you can see here, at high speeds, whether it's Mach 3.5, Mach 4, or Mach 5, you can turn off the detonation engine entirely, and you're full ramjet condition, where you're getting all of that tremendous efficiency and range from the ramjet itself. And so this is our plan. And so here at Venus, right, we are using the detonation engine in a rocket-based combined cycle framework to ultimately transition all the way up to RAM start. And so that's our plan as we are going forward towards making our first hypersonic drone in 2025. We've already flown our supersonic drone here, and so our plan over the next year is to take our detonation engine, put it in the front, Volantra's ramjet engine, put it right here, build up this whole system, put it into a new drone, and go fly fast. Completely showing how this engine is now working, and unlocking the hypersonic economy. So join me on a deeper dive as we go into one of these topics or on the next episode of our high-speed flight series. Thank you.